We're going to continue with our, I guess program is the right word. Andrew Myers, another of Barbara's former students, is next up. Andrew? I know he's here. I saw him earlier.
Yeah, don't applaud until you hear what I have to say. So hi, I had the privilege to be one of Barbara's students in the 90s, and actually we're still collaborating, so that's a lot of fun. I was asked to talk about Barbara's contributions to programming languages and programming methodology, so this is going to be a more technical talk than the previous ones, so please forgive me. So I actually came to MIT originally because I really loved her work on Clue and Argus, the programming languages. And and as you know, her Turing Award citation talks about that work, and particularly her work on data abstraction, which has really profoundly affected the way that programming languages are designed and the way that software is built today. So I was, of course, very proud when Barbara got this award, and I looked around on the web to see what people were saying about it. And there were some interesting reactions out there. So one thing that I read was somebody posting, why is this worth a Turing Award? Everybody knows this stuff. And of course, there was an immediate response, which was, you idiot, that's why it's a Turing Award. So Barbara's ideas are so fundamental that they're baked into most modern programming languages and into how programming is taught. And it's interesting, though, what you find when you teach these ideas is that they're actually a little counterintuitive. Because programming languages are supposed to be about giving programmers the expressive power to get things done, right? And yet data abstraction is actually in some sense about taking power away from programmers. It's about preventing them from doing things for their own good. So this is a key insight that's embodied in the Clue language. That programming languages ought to be designed in such a way that they prevent programmers from breaking these data abstractions, from violating the abstraction barrier. So why is this an important insight? Well, these abstraction barriers allow us to manage complexity, because abstraction barriers let us break systems into components that we can then design and evolve relatively independently. And that is important, and that's why programming languages that are aimed at building large software systems all have this idea of data abstraction baked into them. Now, computer science is not the only discipline in which complexity is an issue. But I would argue that we're the discipline that has the best answers about how to manage complexity. And Barbara's work, of course, is central to that. So, for example, who else confronts complexity? Well, one example is the discipline of systems engineering. So systems engineers worry about how you can compose together systems of systems where the systems are not only computers and programs, but also involve work by civil engineers, mechanical engineers, and so forth. And if you look at, so clearly they're confronting complexity, and if you look at what they teach and listen to what they say about how to manage complexity, it turns out that what they're telling you is it's about abstraction, and the ideas are ideas that come directly from programming languages and software engineering, and they use a lot of the same words. So I would argue that Barbara's influence extends beyond computer science to other disciplines. Now, I've been talking about data abstraction, but this is really just one of her important contributions to programming languages. If you look at the Clue language, you find that it's full of great ideas. There are a number of firsts in it. Not only really enforcing data abstraction at the programming language level, but it's also the first language that gets type-safe constrained generics right. It's the first language that had type-safe variant types. It's the first language that gets exceptions right. Actually, very few languages still get exceptions right. And so these ideas in CLU actually influenced most programming languages that you've heard of. And beyond CLU, she also, her group also developed the Argus language. This was also a groundbreaking language that showed that you could raise the level of abstraction for building distributed programs, and you could integrate transactions into the programming language. And then with Jeanette Wing, they developed what's called the Liskov substitution principle, which illuminated what subtyping is really all about and what it means to build class hierarchies that make sense. And so if you look at applications that are built today, you'll discover that typically modern applications are built in object-oriented languages, which are enforcing data abstraction, and they're using language-integrated abstractions for distributed programming and for persistence. And Barbara was a pioneer on all of these things. So, looking at her work, I think the reason for her impact was that she was just amazingly prescient about what programmers were going to face in building systems. And really thinking about the real problems, the methodological problems that programmers would face and how to capture that in programming languages. So I've thought a bit about what Barbara's secret sauce was, and I have to admit I don't know. It's still secret. But other people who spoke before me said some very illuminating things, which I wish I had thought of. But here are a couple of things that I notice. Barbara is really, she's always about the ideas and getting to the bottom of things deeply. And she's also incredibly good at identifying the right problem. It's that prescience that I mentioned again. And she also has an amazing ability to find the simple, clean solutions that really solve problems. So thank you, Barbara. You've been an inspiration to me and I think to all of us.